Okay, so let us see the next section. This is the slide which talks about the mechanical properties in the copper nickel system. Okay, like the copper nickel alloy, it is there. So it is seen that in copper, this is your copper here, and we are adding nickel. So the composition in terms of nickel is written like 0%, 20, 40, 60, 80 and 100. So this is the composition of nickel. Okay, at this extreme point nickel will be your 100%, and at this extreme point the copper will be your 100%, right? Okay, copper will be 100%. Why? Because the nickel is 0%, that means it is of copper. So as we are adding the nickel, okay, so this is forming a substitutional solid solution and it is increasing the strength. Okay, so the substitutional solid solution basically increases the strength. It is increasing up to the point somewhere here, and if you see, then it is touching around the 60% nickel it is. Okay, then it is decreasing. Okay, because you see, up to this point you can assume that the addition of nickel basically is enhancing, but after this point when the nickel percentage is more, then it is more like nickel has the uh, matrix, and there we have added the copper because the more percentage of nickel is there, right? So this is, so once we have the strength higher, then the ductility will be lower. So that's what here it has tried to explain. So see, percentage elongation, that tells you about the ductility. So that is lower at this 60, right? Then it increases. Okay. So these are two relation. So that is well explained over here. Now see, the binary phase diagram. Let me add some more slides over here so that I can explain you. Okay, see, binary phase diagram. Okay, so binary means two component it will be, right? So it will be something like this, where we will put temperature in one side and percentage B in one side. Okay, so this will be made up of A and B, right? And there will be different phase diagram, different things. Okay, now one is the eutectic phase diagram. Previously we discussed this isomorphous phase diagram, right? Isomorphous, where we had drawn something like this, right? This is your temperature, then percentage B. So similarly, there are some other standard kind of phase diagram. So this is eutectic phase diagram, right? So in the case of eutectic, what is there? It is something like this. You can, there is a straight line, okay, and there is a straight line such that above of this top line, this is the line, we have the liquid over here. Okay, this will be the liquid, and this is your alpha, this is your beta. Alpha is the solid where we have this A rich, that means here we have maximum A and least B, right? So A here it is 100% A and B is 0%, right? So B here it is 100% and A here is 0%, right? So A okay, so B moves like this and A moves like this. Okay, so the reason here it will be rich in A, right? So alpha is a rich region, A type of atom is more, and beta is B rich region phase. Okay, so this is alpha, so it will be, so how do you know name it? Because it is alpha, so it is the boundary between alpha and this, so just we will write alpha plus L. So you can also see this is your L, so this is the boundary, so the L should come just near. Okay, and here it will be, here it will be alpha plus beta, and this will be L plus beta, this region. Okay, so generally this eutectic phase diagrams looks like this, and this is the point of eutectic. So eutectic, you can remember that the transformation which happens, the liquid gets transformed to two phases, that is alpha plus beta. So you can see when we are cooling it, so initially it is the liquid and it is transforming at this point to directly alpha plus beta, right? So that's what this is the eutectic point. So this composition will be eutectic composition, and this temperature, this is the very straight line. Okay, so that means it happens at a fixed temperature, and the temperature is called as eutectic temperature. Okay, so that's what here it is given. This is copper Ag, so you can see that this is diagram somewhat looks like this. This is alpha and beta, right? This is liquid plus alpha, then liquid plus beta, and alpha plus beta. Okay, but here actually you should write here alpha plus liquid, then it is right. Liquid plus alpha, it will create a confusion. Okay, so see, alpha, it is mostly copper, so because here it is copper and Ag, and beta mostly Ag, right? No liquid below this Te. So this is your eutectic temperature. This is the straight line one, because below this everything is solid, right? This is composition Ce, that means composition at eutectic, it is written. Then eutectic reaction is the liquid is getting transformed to this alpha and beta, right? So we can write here alpha and beta. Okay, okay, now when it is transforming, now it is at this point. Okay, this is the point, right? This is the point. So what is the composition of liquid alpha and beta? Okay, so liquid is here, this point. So liquid will have the composition this Ce, and alpha it is in touch over here, so alpha will have composition like this, so that's why alpha it is 8%, and beta it is in touch over here, so the composition will be 91.2%, 8% Ag, right? You remember, this is just the composition of that liquid and the solid which is forming. Okay, no problem. Next, similarly, this is PbSN eutectic system, means lead tin. This is a very important alloy because it is used in electrical application, where when we join two wires, then we put this thing over there. Okay, so you can see, suppose someone asks you at this point what is the composition, it will be alpha plus beta, right? What will be the composition of alpha and beta? So alpha it will be it will be touching this alpha line, so alpha and beta here, right? Now what is the relative amount of phases which will be over here? So relative amount of phases, so since it is alpha, now we need to find the weight fraction. Okay, so alpha, it is in the left side, so weight alpha, it is written. So this is the left hand side phase we need to find, so that we will take the right hand side, this arm, right, tie line arm, so it will be S divided by R plus S, right? So it is given. So S will be this C beta, this line, this point minus this point, okay, divided by this C beta minus from initial, that is C alpha, it is given. Similarly, W beta, weight fraction of beta, it is in the left side because we have written alpha plus beta. Na? Always you write, because alpha it is in the left hand side, so we will write alpha, beta it is right hand side, we will write alpha plus beta, because if you write beta plus alpha, then it will be confusion. Okay, so beta it is in the right hand side, so here we can do the left hand side one, will take the left hand side arm r divided by this total. Okay, so we have got this thing. So it is very easy to calculate once you understand. Now similarly at 220 degrees centigrade we need to find. Okay, so we have the composition here alpha L plus L, right? That's why I told you to write here alpha plus L, otherwise it will, because it is written opposite, right? Just the composition here, if someone asks you the composition, then this is the point, then composition of alpha will be the touching this line, so whatever it is 17 here, and here it is 46, right? Now similarly weight fraction of alpha, right? So this is your alpha, so that means this is your alpha, so this is in left hand side, so we'll take the right hand part, that is S. So S is nothing but this CL minus C naught, so that's what it is written, CL minus C naught, S by R plus S, right? So this WL, what will take, because liquid it is in the right hand side, so we will take the left hand part, that is R divided by R plus S. Simple. Okay. Okay. This is the same phase diagram, only this section has been taken, like this section it has been taken. Okay, see up to 38% it is given. Now here it is trying to tell you, means how the microstructure it will vary. Suppose I take for alloy which has got this much percentage of this tin. Okay, so initially at this point here it is given, so it is completely liquid, fine, no problem. Now at this junction what happens, small amount of alpha will start forming, right, because this is the first line it will touch. Now when it will come to this point again, then this alpha whatever it is formed, that will be there, and the remaining liquid which is there, that will also getting transformed to alpha. Okay, so now similarly for this, suppose someone asks, so here initially it will be liquid, right? Then we have the liquid plus alpha, then we will have complete alpha, then from this alpha the beta will nucleate, so this will be beta, beta smaller, red, so it is there, right? Okay, now how the microstructure will develop in the eutectic case. Okay, so this will be complete liquid, then here you can see that alpha and beta it has formed the blue one and the red one, and this is in alternate layer, right? So it is somewhat like this. alternate layer, right? So this is also called as this lamellar structure. You will further study that this lamellar structure is also seen in some other case also. Okay, so this is the live example. That means this is the microstructure which is given. It has been taken from the material. Okay, so you can see so how this alpha and beta looks like. So this is this alpha line, red one, then blue one, this is beta. So this is alternate layer, right? So like this white line maybe you can consider like alpha, and this black line you can consider like this beta. Okay, okay, next system development in 4. So here it will be liquid, then it will be transforming to this liquid plus alpha. Okay, liquid plus alpha, then more alpha it will be there, right? Then after this point, so what happened, liquid plus alpha is there, and the next whatever the liquid it is, so that will transform to alpha plus beta. So we will have microstructure like we have alpha beta in the alternate layer, and we have some places where the extra alpha is also there, right? Okay, so this is the microstructure you can see for this region, because in this region what is there, we have the alpha plus beta. Okay, but also this is the point where we have the eutectic, right? So there will be some percentage of eutectic, and this alpha plus beta at this point is the complete eutectic, and as we go towards this, so there will be some alpha phases also, and this is the eutectic, and if you go towards this, then there will be extra beta phases. Okay, so this is, we are towards the left, so we have this uh, lamellar phase, and along with that we have this alpha, extra alpha, and for this reason you can see that these are some beta phase or phases also there. Okay, now this is the eutectic point. So below this means just to left, this is called as hypo means lesser composition than eutectic, so it is hypoeutectic. Then above this, then this is called as hypereutectic. Okay, okay, next this is the phase diagram. So this is for mgpb, right? And this is weight percentage of pb, right? So we can see here there is alpha plus liquid. Okay, this is alpha plus mg2 pb phase, this is here beta. So there are some complicated phase diagram it is there, and there is one portion where we are able to see that it is very straight line. So this is one phase, and this corresponds to mg2 pb, right? mg2 pb. So why it is a straight one? Because you see this is mg2 pb, so this is just a compound. Okay, this is just a compound. So a compound has fixed amount of atom of pb, it doesn't vary, because you see in the case of alpha, this is the complete region, right? So alpha can be of this 10 weight percent, pb also 11, 12, 20, then here 30, like this. Okay, over this temperature and this composition, so it can vary, the composition will vary in this alpha, but this mg2b, the composition will be fixed, whatever the amount of pb, that will be fixed. Okay, so this is the compound, so there will be 2 atoms of mg and 1 atom of pb. Okay, so like this. Okay, so this will be one phase. So this is the one phase here, so that's why we have written alpha from the left hand side, and from the right hand side we have taken this alpha plus mg2pb. So similarly mg2b plus beta, here it is written, and here mg2b plus liquid. Okay, now this is another example, copper zinc phase diagram. So you can just see and try to correlate. This is alpha region, then alpha plus liquid, then there are many various regions are there. Okay, this is section of the copper zinc phase diagram. Okay, and this is the point where it is telling you that there is eutectoid transformation. Okay, now eutectic, you learned that liquid once it changed to alpha plus beta, and in the case of eutectoid, so there are basically 3-4 types of reaction. This is eutectic, then eutectoid. It will be one solid will transform to, like solid 1 will transform to solid 2 plus solid 3. Okay, this is eutectoid. And there is one more thing, like peritectic. In the case of peritectic, it is similar to eutectic, but only thing is this one solid will come towards this. Similarly peritectoid, so this solid one, so one solid will come to the left hand side. So these are 4 major reactions. There are other reactions also. So let's see here eutectoid. So eutectoid, that means you understood that one solid should give 2 solids. So here we are able to see that there is delta, and that is giving us this gamma plus epsilon, right? So this is one kind of eutectoid reaction. Okay, and there is this point also, you can see this is gamma plus L. So liquid and solid is there and giving you other solid. So this is, you can say like this is a peritectic reaction. Okay, peritectic transformation. So what are this eutectic, eutectoid and peritectic? So it will say here, this is liquid and changing to alpha plus beta, this is eutectic. Then eutectoid, solid is changing to 2 kinds of solids. Then peritectic, liquid plus solid gives you another solid. Okay, now this is the iron carbon phase diagram, and this is the one of the most important phase diagram in metallurgy or material science. So I think you know about this diagram, means at least you have seen it, right? So this is a typical phase diagram. We have here this gamma, then we have here alpha, then we have here delta. So the 3 forms of iron, we have alpha, then gamma, then delta. Okay, so this is more cleaner. Okay, so we have alpha, alpha plus gamma, then delta. Okay, then gamma plus Fe3C. And one thing is that here the weight percentage of carbon, it is taken up to this 6.7 only, because at 6.7 we get this Fe3C, and beyond that everything remains same, something like this only it will be there. Okay, so there is no need to go very further, it's only 6.7%, to that we can understand. Okay, so iron has basically 3 forms. Alpha, it is at lower temperature, then gamma at high temperature, but delta, it is higher than this gamma temperature. Okay, so there are 3. So this is alpha at low temperature we have, then gamma, then delta, it is there. Okay. Okay, so this is just a small introduction I have given you. So in the next video I will talk about this iron carbon phase diagram completely and also try to explain everything about this. Okay, so thank you.